Hello, good morning, good evening, or good afternoon, depending on where you are. Today we are going to talk about large-scale machine learning. Have you ever imagined how Google handled reverse image search? Even though Google has billions of images, it can return responses in just seconds. That's a very challenging time. The logic behind reverse image search is mainly based on representing images as vectors. The black box here is a regular convolutional neural networks. Google already has the vector representations of those billions of images in its database. But finding the nearest vector among billions is still challenging. This is a famous photographer, Ara Guler. He photographed Hitchcock, Dali, and Picasso in 70s. He declared that if the best camera had taken the best photograph, then the one would be the best novelist who has the best typewriter. It's obvious that Google can handle reverse image search just in seconds, and this has nothing to do with the hardware Google has. The trick is to apply approximate nearest neighbor instead of regular KNN. Spotify Annoy and Facebook Face are libraries to perform approximate nearest neighbors algorithm. In this video, we will apply ANN algorithm on a face recognition task. As a dataset, I'm going to use the unit test items of the deepface library. You can access the deepface library with this URL, and it's under the tests and dataset folder. There are actually lots of facial images, and we are going to use those facial images in our example. I'm going to import operating system library because it has a walk function, and paste the unit test folder of the deepface here. Deepface, tests, and dataset. Here, walk function will return root, its directories, and files. Let's print the files here. As seen, there are some JPEG files and some non-image files. That's why let's build a for loop here. File in files and print file here. Here I'm going to check .jpeg is in file, and if it exists, then print. Also, I have the root variable here. Let's see the content of it. I can access the exact path of a image file just like that, root plus file. This is going to be the exact path, root plus file, and I will not print it anymore. And here I'm going to store them in the facial images list. Let's initialize here before the for loop, and here append the exact path. Let's see the content of the facial images here. We will apply some pre-processing stages of a face recognition pipeline, which are detection and alignment. Deepface can handle those pre-processing stages. That's why I'm going to import from deepface.commons and import functions. Functions module of the deepface has a pre-processed face function, and it expects an image path. Let's fit the first item of the facial images list here. As seen, preprocessed face function returned an array, and let's store it in the image variable. And let's see the shape of the image variable. I'm going to import matplotlib.pyplot as plt to show the image here. Let's call plt.imshow and pass image here, but imshow function expects 3-dimensional array, but it's 4-dimensional. That's why I'm going to fit its first item. That's the preprocessed face of the first item. It detected face and aligned as well. It's in blue because OpenCV loads an image in a reverse format of the RGB. We can handle this just like that. That's the detected and aligned version of the first item of the facial images array. I need to apply this preprocessed face function for all items in the facial images list. That's why I'm going to remove those lines. Here I'm going to build a for loop for face in facial images, and fit a face here instead of the first item, and that's going to be my detected and aligned face. By the way, preprocessed face function expects optionally target size argument, and I'm going to pass here 160 times 160. I'm going to use FaceNet module, and it expects that size of inputs. Let's import the FaceNet module here from deepface.base modules and import FaceNet, and I can build FaceNet module here. Module is going to be FaceNet.load module. In this for loop, I'm going to call module.predict function and pass detected and aligned face as input, and that's going to be my embedding. And let's see the embedding here. FaceNet module returns 126 dimensional arrays, but it has a dummy 1 dimension here. That's why I'm going to pass 0 and all. Let's initialize the representations list before the for loop, and when we got the embedding of a face, let's initialize the representation list and append the file name, which is face here, and also its embedding. This is the key and this is the value. And now append the representation list to the representations list. And I don't need break and print lines anymore. Representation stage is over, and let's see the length of the representations list. There are 61 items in the representations list. That's why I'm going to create some synthetic data. This requires to import random first. For loop for I in range from length of representations, which is 61 to, for example, 100,000. File name is going to be, for example, dummy, and pass the index iteration number here. We can understand if the file name begins with dummy, then that's going to be the synthetic data. I need here embedding size, which was 128. We can understand here. That's the size of an embedding. I also need the minimum and maximum value of an embedding. Let's see the maximum value and its minimum value. I need also this. Here vector is going to be a list. Here I'm going to generate random values, random.goes, and pass the minimum value of an embedding and its maximum value as well, and do this random generation for 128 times for z in range. Here, for example, 128. Here let's initialize a dummy item and append file name and its vector representation as well. And after this I'm going to append this dummy item to the representations list. Synthetic data generation is over, and let's see the length of the representations list here. There are 100,000 items in the representations list. Let's apply a search in those 100,000 items with Spotify Annoy library. Let's import the library first. From Annoy import Annoy index. Now let's initialize the Annoy index. T is equal to Annoy index and pass the embedding size, which is 128. That's the output size of the FaceNet module, and specify the distance metric, which is Euclidean. Now build a for loop and iterate over the representations list for I in range from 0 to length of representations, and get its I index values 1 index value because that's the embedding or vector. Now I'm going to append this vector to the Annoy index t nocta add item, and here I'm going to pass the index value and its vector value. Now it's time to build the Annoy index, and let's pass the number of trees. For example, let's say 3. Now it's time to search. Let's search the 0 index values nearest item in those 100,000 items and find its, for example, 2 nearest items on those vectors. Now I can apply search. Here Annoy index has a get nearest neighbors by item function, and it expects the ID value and its nearest items, here k. This is going to be the neighbors. I also wonder the processing time before calling the get nearest neighbors by item function, and after it let's print the talk minus tick seconds. This function completed in. See the neighbors here, 0 and 2 index values. We looked for the 0 index value, and it's the nearest one is the 2 index values. Let's build a for loop for neighbors. Here remember the representations list store the file name as well. That 0 index value was the file name. Now let's print it. It says that we look for the nearest item of the image1.jpg, and it's the image11.jpg. Let's show those items. Remember the functions module of the div face has a preprocess phase, and it expects file name as input. It's going to be the image, and plt.imshow and image, and its 0 index value, and plt.show. I look for the nearest item of this face, and it's this face in 100,000 items. Let's retransform to its original colors. I fit this face on the above, and it returns the face in the below as the nearest one in a very large vector set. I can increase the k value here. For example, let's set 3 to k. I looked for the nearest faces of the first image, and it returns those faces. They are both Angelina Jolie. The challenging thing is its processing time. It can find the nearest items in almost 0 seconds. That's very challenging time because our vector is very huge. What if we don't have Spotify Annoy in this case? We need to apply brute force. Let's apply brute force search here. Source representation was representations arrays idx items one index value. Let's see the content of it. I've built a for loop for I in range from 1, because 0 index value is the source representation, to the length of representations. Here I index representations lets 1 index value is the target representation. We need to find the distance between source representation and target representation. I need scikit-learn's Euclidean distances module here. Let's see the shape of the source representation here. Is 128 dimension array. Here I'm going to call Euclidean distance function and pass those representations. And this is going to be my distance value. And let's print it. And for example, apply it for the first item first. It returned an exception, and that's because of that it expects just like that 1 times 128 dimensional array. I'm going to append those values. Now it returned an array. I need its 0 index values. 0 index value is 8.1. I need to do it for the all items. That's why I'm going to initialize a distances array and append this distance value here. And after the for loop, I need the minimum values index. That's why I'm going to call numpy argmin and pass distances list here. And this is going to be the candidate index. And let's print it. I actually wonder the processing time. Talk minus tick seconds. As seen, finding the nearest one with brute force method completed in 10 seconds. On the other hand, with Spotify Annoy, it's completed in almost 0 seconds. This means that Spotify Annoy is almost 10,000 times faster than the brute force method. Imagine that if you put this logic backend of a web service, and it will return responses in 10 seconds, which is not acceptable. On the other hand, you can put the initializing Annoy index, adding items and building stages as batch, and you just put the get nearest neighbors by item function backend of a web service. In this way, your web service will return very fast, and this time is acceptable for any kind of service. So we have mentioned how to apply machine learning on a very large scale data sets. Those approximate nearest neighbor libraries can help us with building large scale machine learning models. Thank you all for watching and see you next time.